Welcome to the June 2025, this is the Edexcel A-Level Paper 1. Okay, the first question, f of x plus 2 is shifting it 2 places to the left, so that's going to be 4, negative 4. Y equals inverse f of x, that's swapping the x and the y coordinates around, so negative 4, 6. And then lastly, plugging 6 in, we'll get negative 4 out. The modulus makes it positive 4. Times it by 2 is 8, subtract 3 is 5. So putting 6 in gets 5 out. There's question 1. Question number 2, we've got a circle here. We can read off the centre of the circle, it's negative 3, 4. And we can square root 24 to get the radius, which simplifies to 2 root 6, or you can just leave it as the square root of 24. Either of those is absolutely fine. For B, there's a few ways of doing this. I have calculated the distance from the origin to the centre of the circle. That distance comes out as 5 units. Now the radius of the circle has the square root of 24, which is slightly less than the square root of 25. And therefore the origin is slightly further away from the centre of the circle than the length of the radius. Therefore, we can conclude that the origin must sit outside the circle. Question number 3 is the arithmetic sequence. So we have a common difference here. They're jumping up by the same amount. So the jump from 6k to 10 and the jump from 10 to 2k is going to be the same. It allows us to construct a little equation there. Solve the equation to find the value of k. K comes out as 2.5. For part B, now I've substituted 2.5 into the sequence, so 6k is 15, 2k is 5, so the sequence is the one that goes 15, 10, 5. You can see we've got a common difference of negative 5, the first term is 5. We want to calculate the sum of the first 50, so we have all the information we need to be able to do that. N is 50, so n over 2, lots of 2a, that's 2 times 15, plus n minus 1d, that's 50 minus 1 times negative 5. Plug that into your calculator and you get negative 5,375. Question number 4, I'm going to dive straight in and factorise x plus 4 out of the cubic. To do that, well, we know we're going to need a 2x squared at the front of our quadratic to give us the 2x cubed. Then because we've got 2x squared, if we times that by 4, we'd get 8x squared. We only want 3x squared, so we'll subtract 5x squared, so I'll write minus 5x. 4 times minus 5x is minus 20x. We want minus 16x, so we'll add 4 at the end. If you prefer doing that using long division, that's absolutely fine. For part B, I'm going to calculate the discriminant of the quadratic. So a is 2, b is negative 5, c is 4. Pop that into b squared minus 4ac and calculate the value. It comes out as 25 minus 32, which is negative 7. Negative 7 is significant because it's less than 0, and so we're not going to get any real solutions out of that quadratic. That's the conclusion of the discriminant test. No real solutions come from 2x squared minus 5x plus 4. So the only solutions for this equation is going to come from the x plus 4. And that solution is going to be negative 4. And so we've proved negative 4 is the only real root of the equation f of x equals 0. Question number 5, the limit as delta x tends to 0 of the sum there, that is in itself, the limit is going to be the integral, the exact area. Essentially, we've got an infinite number of infinitesimally small sort of rectangles added together. And so we can just rewrite it as the integral between 1.44 and 2.89 of 2 over root x dx. I'm going to write 2 over root x as 2x to the power of negative a half. To integrate that, we'll add 1 to the power, divide by the new power, so the new power will be a half, dividing by a half is the same as doubling, so the 2 becomes 4, between our bounds of 1.44 and 2.89. Perhaps at this point you spotted 289 is a square number, 144 is a square number. This is going to come out quite nicely. Anyway, I'm going to show that I'm plugging the bounds into the integral, and then that comes out as 2. And so k is equal to 2. Question number 6. The flight of the seabirds. So it gives us 2 points in time after 4 seconds and 9 seconds in their heights. So I'll start by plugging in t to be 4 and h to be 17.6. 4 to the power of 1.5, where we can square root it and then cube it. It's the same as 4 to the power of 3 over 2. You can cube it and then square root it if you want to go the long way round. Anyway, it comes out as 8. So 17.6 is equal to a minus 8b. Then for the second point, plugging 9 in, the square root of 9 is 3, 3 cubed is 27. So 11.9 is equal to a subtract 27b. Gives us a pair of simultaneous equations. I'm going to subtract the second equation from the first. 5.7 is equal to, and then negative 8b subtract negative 27b is 19b. Divide both sides by 19. b is 0.3. We can go back to either equation here, substitute b to be equal to 0.3 into it, and solve it to get our value of a. In this case, I'm adding 8 lots of 0.3 to both sides. A comes out as 20. So our full equation, h is equal to 20 subtract 0.3 lots of t to the power of 1.5. There's our model. For b, well, if t is 0, the 0.3 t to the 1.5 disappears. We get that initial height being 20. The limitation of the value of t, that's the large value, well, at the point where the bird hits the water, let's hope it intended to, I'm going to substitute 0 for the height at that point and solve the equation. And t comes out as, capital T comes out as 16.4 when rounded to 1 decimal place. Okay, on to question number 7. We've got a quartic equation, so we can see we've got 2 repeated roots at -1, 5. Part A is about writing the points where the function's increasing, so it's everything to the left of -1 and everything between 2 and 5, but using set notation. So it's the sets x where x is a real number and x is less than or equal to 1, unioned with the set x where x is a real number where x is in between 2 and 5 inclusive. For all those points, f dash of x will be greater than or equal to 0. Then for b, because we have 2 repeated roots, we can write this as x plus 1 squared times by x minus 5 squared, and then just have a think about what we need to multiply that by to make sure it goes through 0, negative 75. If you think about expanding out the constant parts, we'd end up with 25, so we need to multiply 25 by negative 3 to hit that 0, negative 75. So y equals negative 3 times x plus 2 squared times x minus 5 squared. For c, I'm going to plug 2 in because k can be anything that takes that line down to where the minimum point at 2 is. When I plug 2 into the equation, we get negative 243, so k will be between 0 and 243. Any shift upwards of k will result in 4 intersections with the x-axis. Alright, question 8. The mistakes on the bottom line, when we expand out 5k plus 2 squared, we'll get a plus 10k, which would give me plus 20k. When I factorize out 5, that becomes plus 4k, and similarly, therefore, a plus 4k on the right-hand side. Then to complete the proof, well, we need to cycle through all the possible sort of values of m so that we've covered them all. We've already got 5k, 5k plus 1, and 5k plus 2, so we're going to need to consider 5k plus 3 and 5k plus 4. Once we get to 5k plus 5, we'll be doubling up on the cycle. So we only have a couple more to test. The first one I'm testing is m to be 5k plus 3. If we square 5k plus 3, we get 25k squared plus 30k plus 9. And that's going to be 5 lots of 5k squared plus 6k. And if I put plus 2 at the end, that would give me plus 10. So I'm going to subtract 1 afterwards. And that allows us to write the square number in the form 5n minus 1. And I'm going to copy the format of the way that the question has led and just quote the value of n and give it a tick afterwards. Okay, the last one to consider is when m is equal to 5k plus 4. If we square 5k plus 4, we'll get 25k squared plus 20k plus 20k, which is plus 40k, and then plus 16 at the end. And the plus 16 is important because it's the same as plus 15 plus 1. So I can factorize 5 out of that. If I do a plus 3 just there and then plus 1 outside, well, that is of the form 5n plus 1. And again, to be consistent, I'm quoting the value of n and 5k squared plus 8k plus 3 and give it a tick. And finally, we've got to tidy up the end of this proof just to demonstrate that we understand what we've done. We've covered all of the possible types of square number here, rotating around from 5k, 5k plus 1, 5k plus 2, 5k plus 3, 5k plus 4, squaring them, and when we squared all of those, we could write them in the form 5n or 5n plus or minus 1 for the integer values of n. And then a little square there indicating the end of the proof. Alright, question number 9. Well, we're going to get 2 points where the curve crosses the x-axis. The first one is the obvious one. Well, the factorized version, we can see t equals 0. That's fine, but the other point is going to come when 15 minus e to the 0.2t is equal to 0. Add e to the the 0.2t to both sides. Take natural logs of both sides. Ln of 15 equals 0.2t, or t over 5 if you prefer. Times both sides by 5, and we get t to be 5 ln 15. If you've done ln 15 divided by 0.2, that's absolutely fine. You'll get 13.5 either way, which is the correct value. For B, you will spot that I have mistakenly referred to V as H there. As I have spotted the error, it does not count, do not write in. I'm aware that should be a V, but V equals 15t minus t e to the 0.2t, and then dv by dt will be 15 subtract, and then I'm using the product rule, differentiate t, it differentiates to 1, so we get minus e to the 0.2t, and then differentiate e to the 0.2t gives us 0.2 e to the 0.2t times by the t, we get minus 0.2t e to the 0.2t. Then we want to find the maximum point, so I'm going to set dv by dt to 0. 0 equals 15e to the 0.2t minus 0.2t e to the 0.2t. bring the two expressions with e to the 0.2t onto the left hand side, and I'm going to factorize them out. And then dividing both sides by 1 plus t over 5. And then just to tidy up that fraction, because I'd rather not have a fraction with inside a fraction, I'm going to multiply the top and the bottom of that fraction by 5. So the top 75 and the bottom is 5 plus t. I swapped the t and the 5 around because just looking at where this question is going, they've written t plus 5 at the bottom. Take natural logs of both sides. 0.2t equals ln of 75 over t plus 5. 0.2 is the same as 1/5, so timesing both sides by 1/5, we get t equals 5 ln 75 over t plus 5, which is what the question wanted. Then for ci, it sets up the iterative formula, asks us to start with t1 to be 8. So I'm going to take 8 and I'm going to substitute it into the iterative formula to find t2. If I set 8 into my calculator, hit the equals button, and then do 5 ln of 75 over the answer plus 5, and hit the equals button, we get t2, which is 8.76, etc, etc, etc. And then hit execute again. It saves you having to retype the formula, and we can get t3, which comes out as 8.478. And then you can hit it lots and lots and lots of times to carry out the repeating formula, and you'll see that it tends to 8.55. So the answer to part 2 will be 8.55. Question 10, to find the vector p to r, well, the path we're going to go there is p to q and then q to r. It gives us p to q and q to r in the question, so 2i plus 8j minus 2k, add the 2i plus 6k. And that simplifies to 8i plus 8j plus 4k. Absolutely fine if you've done those as column vectors. For b, I'm going to find the magnitude of the 3 vectors that we have, essentially the side lengths of the triangle. The magnitude of PQ, Pythagoras with PQ, it's Pythagoras in 3 dimensions, so square root of 2 squared plus 8 squared plus negative 2 squared. That comes out as square root of 72. The magnitude of QR is going to be the square root of 6 squared plus 6 squared. And that's also the square root of 72. And lastly, the magnitude of P to R is going to be 8 squared plus 8 squared plus 4 squared, which comes out as a square root of 144. Now the question asks us to show that PQR is both right-angled and isosceles, and so by stating that P to Q is equal to Q to R, our triangle has 2 side lengths that are the same. That means that we're dealing with an isosceles triangle. And then for it to be right-angled, it has to work with Pythagoras' theorem. So PQ squared plus QR squared is equal to PR squared. (72 plus 72 equals 144). And therefore, we can conclude that this is indeed a right-angled triangle. Okay, question number 11. This is constructing a model for the value of a car. It tells us the initial value is 20 grand, so we're going to substitute that one in. T is going to be 0. That means that e to the power of minus kt is going to become e to the power of 0. E to the power of 0 is 1. And so we can subtract 1,500 from both sides of that, and a times 1 is just a, so a is going to be 18,500. Then at the point when t equals 2.5, the value is 12,000, so substituting both of those into the equation, 12,000 equals 1,500 plus 18,500 times e to the power of minus k times 2.5. Then subtract 1,500 from both sides. Divide both sides by 18,500. It simplifies down to 21 over 37. And then we can take natural logs of both sides. I've swapped them around just to bring k onto the left. And then divide both sides by minus 2.5 or an equivalent. And then when you plug that into your calculator, you'll get k to be 0.227. And then to answer the question directly, it wants a complete equation for the model. So v equals 1,500 plus 18,500 e to the power of negative 0.227 t. All right, part B, we want to find the rate of change. So that's telling us to differentiate. So we are going to, it actually gives the answer in terms of k. So I'm going to revert back to the version of the equation with k in it. So v equals 1,500 plus 18,500 e to the minus kt. Differentiating that with respect to time, so dv by dt, the 1,500 will disappear, and then we'll multiply by minus k using the chain rule, or maybe you've just learned that when you differentiate a multiple of your variable, you times by the multiple when it's e to the power of it. Either way, we get minus 18,500 k e to the minus kt, and I'm writing that as minus k times 18,500 e to the minus kt, because that allows me to do a little substitution. I'm going to take the original equation, subtract 1,500 from both sides, so v minus 1,500 is equal to 18,500 e to the minus kt, and therefore I can substitute 18,500 e to the minus kt for v minus 1,500. So we get minus k times v minus 1,500, which is what the question wanted us to show. Then for C, there's any number of answers. There are so many limitations to this model. Cars will break down. You can say that if a car gets scrapped, its value is going to go below 1,500. The model assumes that the car depreciates in a really consistent way, which is not the way things work out. Any valid critique of this model is sufficient. I've gone with the car may break down or have an accident, and its value may go under 1,500, but the model does not allow for this. Okay, on to question number 12. Question number 12, it asks us to verify, command word verify. It means you can use the fact that it's true. It's different to show that. If it says show that, you cannot. But to verify something, we can take our value x equals 6 and we can just plug it into both equations. So plugging it into the first equation, 15 times 6 over 2 times 6 plus 3 times 6 minus 3. That comes out as 2. And then when you substitute 6 into y equals 2x minus 10, you get 2 times 6 minus 10, 12 minus 10, which is also 2. And because both of those are 2, we know that these two lines will meet at 2, 6. They meet when x equals 2. Then for b, to find the intersection of the line and the curve, we're going to substitute y for 2x minus 10. So 2x minus 10 will be equal to 15x all over 2x plus 3x minus 3. And the solution to this equation will give us the points of intersection. So we are just going to rearrange everything. I'm going to multiply both sides by 2x plus 3 times x minus 3. So we bring that 2x plus 3 and the x minus 3 up onto the left-hand side. That's going to be equal to 15x. And then we're expanding out the brackets. So I'm going to expand out the first two brackets. So 2x minus 10 times by 2x plus 3 gives me 4x squared minus 14x minus 30. That many lots of x minus 3 will be equal to 15x. And then multiply each part of the quadratic by x, and then by minus 3, and then collect them. It gives us 4x cubed minus 26x squared plus 12x plus 90, and that's equal to 15x. And then lastly, subtract 15x from both sides, and you get the equation that they wanted us to show. (4x cubed minus 26x squared minus 3x plus 90 equals 0. For C, you could do some long division to divide by x minus 6, because we know that's one of the factors. I'm just going to factorize the cubic straight away, so x minus 6 lots of 4x squared minus 2x minus 15 equals 0. We know x equals 6 is the solution, but that's not the one we want. We're going to get two solutions from the quadratic, and I'm going to look for the lower of the two, so the subtraction when using the formula, because that's going to give me the x value to the left, because there's two other intersections of the line and the curve we can see on the diagram. So I'm going to take the negative square root, and I'm plugging the numbers into the quadratic equations formula. Minus b plus or minus the square root of b squared minus 4ac all over 2a. Plug those in, we get x equals 2 minus 2 root 61 over 8, which simplifies to 1 minus root 61 over 4. And that is the exact x coordinate of the point Q. Question 13, integration by substitution. So I'm going to use substitution u equals 2x plus 1. Differentiate that, du by dx equals 2. And then the purists will not like what I've done here. I've treated du by dx as a fraction, which of course it's not. But I'm rewriting that as a half du equals dx. Then plugging the boundaries into the substitution. So when we plug 2 in, we get 5 out. When we plug 0 in, we get 1 out. So we're now going to be integrating between 1 and 5 rather than 0 and 2. We're going to do a little rearrangement of the substitution just to deal with the x at the top. So making x a subject, we'll get u minus 1 over 2. And I can rewrite that x then as u minus 1 over 2 in the integral. That's going to be all over x cubed, so I'm going to bring that up straight away as u to the minus 3, and then I'm going to replace dx with my half du from earlier. Then I'm going to take the constant part, I'm going to take a quarter out, that's the 2 from underneath the u minus 1 and the half at the end. Put them together to make them a quarter and take them outside the front of the integral, and then expand out the bracket. So u times u to the minus 3 is u to the minus 2, and minus 1 times u to the minus 3 is u to the minus 3, and we can integrate one at a time, add 1 to the power, divide by the new power. We get u to the minus 1 over minus 1, and then subtract u to the minus 2 over minus 2 between 5 and 1. I'm going to tidy that up before substituting the numbers in. So u to the minus 1 over minus 1 is the same as minus 1 over u. And then the two minuses cancel on the second one, and we're left with 1 over, that should be 2u squared. There's another mistake for you, but I've spotted it, so it doesn't count. No rewards for writing in on that one. Anyway, fortunately, I've remembered to do 2u squared when I've plugged in my 5 and when I've plugged in my 1. So I've got away with the mistake, and it's going to be a quarter. Simplify everything, we get minus 9/50ths from the first one, and plus a half, which is a quarter of 16/50ths, and that simplifies to 2/25ths, which is what the question wanted. Alright, question number 14. So sine of x plus 30 plus root 3 lots of cos of x plus 30. You can, if you like, if you wanted to, you could do a substitution, y equals x plus 30. Some people prefer doing it that way, and then reverse the substitution afterwards. I'm not going to. I'm just going to leave the x plus 30 and treat it as its own object. And so I'm going to compare the expression with my expansion for r cos of, and then x plus 30 plus alpha. So it's the same as r as x plus alpha as it normally is. So it's going to, expanding that out using cos of a plus b, we get r cos of x plus 30 cos alpha minus r sine of x plus 30 sine alpha. And then the r cos alpha, that's going to be equal to the root 3, because it's next to the cos x plus 30. And then minus r sine alpha will be equal to 1. I'll bring the minus over to next to the 1. So r sine alpha equals minus 1. Tan alpha will be the sine alpha over cos alpha, so minus 1 over root 3. And we can deduce, therefore, that alpha must be negative 30. My r value, well, I've squared them both and square rooted. So square root of 3 squared plus negative 1 squared. That's going to be root 4, which is 2. And so what we've done is we've shown that sine of x plus 30 plus root 3 of cos of x plus 30 is going to be equal to r cos, and then x plus 30, well, we know r is 2, x plus 30 plus alpha, we know that alpha is minus 30, so it's 2 cos x plus 30 minus 30, and that's equal to 2 cos x, which is what the question wanted us to show. For part B, we can use our identity from part A to simplify it all down. So the whole of sine of theta plus 30 plus root 3 cos of theta plus 30 we can rewrite immediately as 2 cos theta. That's going to be equal to the 3 sine 2 theta on the right hand side, and using sine of 2 theta equals 2 sine theta cos theta. The right hand side will become 6 sine theta cos theta. Don't be tempted to divide by cos theta here, you'll lose the solution. So bring the 2 cos theta onto the right hand side and factorize out the cos theta, or 2 cos theta. So we get 0 equals 2 cos theta, 3 sine theta minus 1. Then we get 2 sets of solutions, one where cos of theta is equal to 0. That gives us theta to be 90. and the other one is going to come from sine of theta being equal to 1/3. And the two values of theta within that range are 19.5, and then to get the other, subtract 19.5 from 180 to get 160.5. And then it's nice to write your solutions in ascending order. So theta equals 19.5, 90 degrees, and 160.5 degrees. Question 15. Well, it tells us that the area of this shape is 240. So I'm going to start with constructing an expression for the area. There's my theta, my 2 r's, and my 1/10 r. Well, the area is going to be, using my radians formula, theta over 2r squared. Plus, and then a 1/10 r times r is a 1/10 r squared. That's going to be equal to 240. Then I'm going to make theta the subject of this equation. So divide everything by r squared. You can factorize the r squared out first and then divide it if you wanted to. So theta over 2 plus 1/10 is 240 over r squared. So theta will be equal to, I'm going to bring the 10th onto the right, subtract a 10th from both sides, and then times everything by 2. So 240 goes to 480, and 1/10 goes to 1/5. Now the expression for the perimeter, we're going to have theta r as the arc length, and then we've got plus the 10th r on either side, so it's 2 lots of the 10th r of the rectangle, the r from DC and the other r from AO. That takes us right the way around the outside of the shape, and then we can substitute our expression for theta. So theta is 480 over r squared minus 1/5, so it's that many lots of r. And then we're going to get a 5th r plus r, so that's going to be 11/5 of r. And then expand it out, so 480 over r squared times r is 480 over r, minus a 5th r plus 11/5 r, that's going to be 10/5 r, well that's the same as 2r. So our perimeter will be 2r plus 480 over r. For part B, we want to find a stationary value, so that's telling us to differentiate. I'm going to rewrite the 480 over r as 480 r to the minus 1. Then dp by dr, the rate of change of the perimeter with respect to r. Well, the 2r will differentiate to 2, and the 480 r to the minus 1 will differentiate to minus 480 r to the minus 2. We'll set dp by dr to be 0, because we're searching for a stationary point, and then 480 r to the minus 2, I'm going to rewrite as 480 over r squared. Bring that onto the left hand side, 480 over r squared equals 2, times both sides by r squared, divide both sides by 2, we get r squared equals 240. So r is equal to the square root of 240. You can calculate that if you want to, I'm going to leave it as an exact value. Then for part C, we want to prove that this is a minimum point. So the further differentiation instruction is a little bit of a hint there. It's asking us to differentiate again. So d2p by dr squared. 480 r to the minus 2 differentiates to 960 r to the minus 3. When I substitute the square root of 240 into that, we get 960 over the square root of 240 all cubed. It comes out as 0.258, which is only interesting because it's greater than 0. And that means that we are indeed dealing with a minimum point. Do state that it's greater than 0. It's that fact that it's greater than 0 is the thing that implicates us having a minimum. All right, on to question 16. We have another another substitution to do here. So x equals 2 sine u. If we differentiate that, dx by du will be equal to 2 cos u. Okay, we're integrating between 1 and root 3 here, so I'm going to run those through the substitution, set x to be 1, so sine u will be equal to a half, u will be equal to pi over 6, and then set x to be root 3, sine u will be root 3 over 2, so u will be pi over 3. So our new boundaries will be pi over 3 and pi over 6. The purists will dislike me again. I've split dx over du into dx equals 2 cos u du. We're going to be integrating between pi over 6 and pi over 3. The expression 1 over then x squared is going to become 4 sine squared u. And that's then the square root of 4 minus 4 sine squared u. And times by 2 cos u du. Okay, I'm going to simplify the square root of 4 minus 4 sine squared u. We can factorize out of 4, it's 4 lots of 1 minus sine squared u. 1 minus sine squared u is of course cos squared u. So that denominator will become the square root of 4 times the square root of cos squared u, while the square root of 4 is 2 and the square root of cos squared u is cos u, and everything else I've left alone. The two cos u's will cancel really nicely, and so we're left with the integral between pi over 6 and pi over 3 of, and then it's going to be, well, it would be 1 over 4 sine squared u, but that's of course a quarter cosec squared u, to write it in the form that the question wanted us to. Cosec squared u will integrate to minus cot u. You get that in the formula booklet if you forget it. So it's going to integrate this one, the quarter is still there, minus a quarter cot u between pi over 3 and pi over 6. Now if you know cot of pi over 3 and pi over 6, you can just substitute it straight in. If you need to reverse engineer the cot to cos over sine, we're going to get cos of pi over 3 over sine of pi over 3, and then cos of pi over 6 over sine of pi over 6. I've taken the minus quarter out the front just to keep it a bit tidier. Cos of pi over 3 is a half, sine of pi over 3 is root 3 over 2. Then cos of pi over 6 is root 3 over 2. And sine of pi over 6 is a half. So we've got a quarter. A half divided by root 3 over 2 will simplify to root 3 over 3. And the root 3 over 2 divided by a half is going to simplify it to root 3. Root 3 is the same as 3 root 3 over 3 to give it a common denominator. And so root 3 over 3 minus 3 root 3 over 3 is minus 2 root 3 over 3. And lastly, I'll finally multiply by the minus quarter to get root 3 over 6 as the exact area. Well done if you got that one. All right, bye.